Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today's speaker is Lionel Levine, and he'll be talking about the scaling limit of Diaconis-Fulton addition.
Thanks, Henry. So this talk is going to be on joint work with Yuval Peres. Okay, so what is Diaconis-Fulton addition? So say we're given two finite sets in the integer lattice ZD, which have some intersection, and let's label the points of the intersection x1 through xk. And we're going to form a new set, which we call A plus B. And this is going to be a random set. And the way it's formed is, so first start with the union of A and B. Call that C0. And then for each point, of the intersection, run a random walk until it exits the set of points which have been occupied so far. So if here's x1, we run a random walk until it reaches a point outside of the union of A and B. We call this point y1. Then we take our next point in the intersection, x2. We run a simple random walk until it exits the union of A and B and y1. We call that point y2. You do this for all the points of the intersection, and you'll get some random set, and that's the set that we're going to call A plus B. And the key property of this operation, which makes it something interesting and worth studying, is, so it turns out that the law or distribution of this random set doesn't depend on the order that you chose for your points x1 through xk. So you can run these walks in any order you like, and the resulting set will have the same distribution.
Why? Is that easy?
It's fairly easy. So there's actually a really large class of models that all share this Abelian property. This was first noticed by Diaconis and Fulton. So I'll talk about some of those other models in a second. So here's a picture of what you get if A and B are two squares which overlap in this smaller square in the center. And the red points are the points y1 through yk. So one special case of this, which is particularly interesting, is called internal DLA. DLA stands for diffusion limited aggregation. So imagine taking just the singleton set consisting of the origin and repeatedly adding that to itself. So if you do this n times, you'll get some region in ZD consisting of n points. It's a random region. And so this model was studied in the early 90s by Lawler, Branson, and Griffith, who showed that the limiting shape you get is a ball. So more specifically,
Can you explain the process again?
what is the model?
The process.
Yeah. So So we're going to start with the set A1, which just consists of the origin. And then we're going to given the set an minus 1, we start a random walk at the origin and let it run until it exits an minus 1. And let's call yn the point where it exits. And we define an, sorry, these are backwards. We define an to be the union of an minus 1 with this boundary point. So intuitively, if your set wasn't shaped like a ball, then it's quite likely that your walk will hit this indentation here, and somehow the boundary, if it has fluctuations, they're going to get gradually smoothed out. Is the model clear? Okay, so what exactly did they show? Well, let's say you start with n particles, where we're going to write n as omega d r to the d, where omega d is the volume of the unit ball in rd. So if we start with this many particles, we should expect our set an to be approximately a ball of radius r. And they showed, well, it's with probability 1 for r large enough, it's squeezed in between two balls of slightly smaller and slightly larger radii. So here's a picture of what you get with 1,000,000 particles, and you can see it's quite round. There's just very small scale fluctuations on the boundary.
What are the colors?
So the colors aren't directly relevant to the way I've described it. So there are 4 colors, and they represent the direction in which a particle last exited a site. So another thing that's interesting to study is, well, what happens if instead of using random walks to define these models, we use some other process? And one particularly fascinating process is called the rotor-router model, which is a deterministic analog of random walk. So this was originally defined in the physics literature by Prijev and others, and then it was reinvented or repopularized by Jim Propp several years ago. So the way this model works, I'll describe it in Z2. You have, at each site in Z2, you have a rotor, which is just an arrow pointing to one of the 4 neighboring sites. You start a particle at the origin, and when it comes to a site, it does 2 things. It first rotates the rotor clockwise by 90 degrees, and then it takes a step in the direction of that rotor. And just as with internal DLA, we can make this into an aggregation model where we start with the region A1 consisting of only the origin, and we form a sequence of regions AN where so AN is the union of AN minus 1 with a single point, which is the endpoint of a rotor-router walk, which starts at the origin. At xn, the point that you add, is the point where it first leaves the region AN minus 1. And so I described this in Z2, but you can also do this in higher dimensions. Instead of cycling through the 4 neighbors in some fixed order, you can cycle through the 2D neighbors in some fixed order. So let me show you a simulation of this. So we're going to start with all the rotors pointing north. this black box represents the location of the particle. So the particle rotated the rotor 90 degrees, and now it's going to step in that direction. And it's reached already an unoccupied site, so now that site will become occupied. And now we're going to start a new particle at the origin. It'll rotate the rotor and then step. We start a new particle at the origin, rotate, step, new particle, rotate, step, new particle, rotate, step, and now this site is already occupied, so we need to keep walking. So we're going to rotate again and then step. And now we've reached an unoccupied site. Stay there. And so on. So let me speed this up. So the first thing you notice is, as with internal DLA, when we were running random walks, we also get a very round-shaped region. So there's the question of why this is. And then you can also start to see some interesting patterns forming, especially near the boundary here. So you can ask questions about that. So here's the region you get from a million particles. And so the first question about this was, why is it so round? So here's what we can show. So if we let AN be the region of n particles that are formed in this way, then we can show that so AN is squeezed in between two balls. And so what are the radii of these balls? So if we choose R so that n is omega d r to the d. So a ball of radius r has volume n. So that's how big we expect the radius to be. And then we can show that this set AN of occupied sites, so it contains a slightly smaller ball where you only have to go in by a constant times the log of the radius. And it's contained in a somewhat larger ball where you only have to go out by some smaller power of r. And so one succinct way to state, well, a somewhat weaker result, but it's much shorter, is to talk about the ratio of the in and out radius. So we say that the in radius of a set is the distance from the origin of the closest point not in the set. The out radius is the distance from the origin of the furthest point that's in the set. So in particular, this result implies that the ratio tends to 1. Okay, so what else can we do with this? Well, we can also try running Diaconis-Fulton addition. So here we've started with two squares. And we've taken, so they intersect in this light blue square in the middle. And we've started a rotor-router walk at each point of this intersection and run it until it exited the union. And it exited at these red points. And so the shading in this picture represents the 4 rotor directions. So one question you might ask about this picture is, does it matter in which order we perform these walks? Because that was important for the Diaconis-Fulton addition, that we could perform them in any order. So it turns out that it doesn't. So this is a simple property of this rotor-router model. And so it shares this property with something called the Abelian Sandpile model, also called chip firing. So the way this works is, instead of particles, you can think of grains of sand occupying points of the lattice. And if you're in Z2, if a site accumulates 4 or more grains of sand, it'll topple. And toppling just means it sends 1 grain to each of its 4 neighbors. And this is called the Abelian Sandpile because it has this property that you can choose, maybe you have several unstable sites. You can choose to topple one site, and this might create an avalanche of topplings when other, its neighbors might become unstable and so on. And then after this avalanche dies out, you can topple another site, and it may cause some avalanche. And these two operations commute, so it doesn't matter in which order you did the topplings. So one consequence of this Abelian property is you can describe these models in a somewhat different way. So let's start with n particles at the origin. But now our toppling rule is going to be, let's say that some site has m particles. Then we're going to take, so we're going to divide m by 4. And we get some quotient and remainder. So we're going to send floor of m over 4 particles to each of the neighbors. And we're left with some remainder mod 4. And in the sandpile model, we just leave this remainder between 0 and 3. We just leave it in place. On the other hand, for the rotor-router model, we're only allowed to keep 1 particle at every site. So if there's a remainder mod 4, we're going to send the extra particles to the neighbors according to which direction the rotor is pointing. And it's a simple consequence of this Abelian property that if you run the model using these rules, you'll get the same final state. And so one thing you might think, now that we've phrased it in this way, is that, well, rotor-router and sandpile should give you more or less the same thing because there's just these little rounding errors. That's the only difference between the two models. But if you think that, then it turns out you're wrong. So here's a picture of the Abelian sandpile if we start with 1,000,000 particles at the origin. And so one thing you immediately notice is that it doesn't appear to be circular. So it has these straight sides. So somehow these little errors that we're incurring in the difference between the two models actually add up to something substantial. Okay, so this isn't circular, but what can we say about it? So let's let Sn be the set of sites that are visited by the Abelian sandpile if we start with n particles at the origin. So then we can also squeeze this set between two balls. But the ratio of the radii of these balls is not going to tend to 1. Because, well, it's not known, but probably in the limiting shape isn't a ball. Certainly doesn't seem to be by the pictures. So specifically, we can squeeze Sn between a ball of volume about n over 2d minus 1 and a ball of volume about n over d. So this improves some earlier bounds due to Le Borgne and Rosen. So here's a picture of all the known bounds. So this blue part sticking out is the actual occupied set. This yellow diamond and this outer square are the Le Borgne and Rosen bounds. and then this inner disk and outer disk are the bounds that we can prove. So we don't know what the set is. We don't even know if the limiting shape exists. But whatever it is, it's always sandwiched in between these two disks. Okay, so there's one more model I want to talk about called the divisible sandpile. And this model is somewhat different from the others in that it works with, instead of discrete particles, it's going to work with continuous amounts of mass. So we're going to start with some amount of mass at the origin. And then the mass is going to move around according to the following rule. So each site will keep mass 1 for itself. And if it ever gets mass more than 1, it will just split the excess mass equally among its neighbors. So if you run this model for a long time, well, so it's never going to, you're always going to have a very small amount of mass that's still moving around. But the amount that's still moving around tends to 0 as the number of topplings you perform goes to infinity. So in this limit, as t goes to infinity, you're going to get some region, which we'll call AM, of sites in the plane which are fully occupied, so they have mass 1. And then on the boundary of this set AM, you'll have some sites which have fractional mass, so something strictly between 0 and 1. And then outside this boundary, which just has width 1, everything will have mass 0. Okay, so what can we show about this region AM? So it turns out that this model is in many ways the easiest to work with, and we can show correspondingly sharper bounds for it. So in particular, so there are two balls whose difference in radii is just a constant independent of the total amount of mass. And the set AM is squeezed in between those two balls. So here's a picture. This is starting with mass 100,000 at the origin. And it's just shaded to make it more interesting. It's shaded according to, so at each site you look at the total amount of mass that site emits, and you look at its fractional part. And you color it grayscale according to that fractional part. So here's a picture of a Diaconis-Fulton sum that was computed using the divisible sandpile. So in this picture, what we've done is we start with mass 1 on this blue region and mass 1 on the green region, and mass 2 in this light blue square. And then we've relaxed it and obtained a larger set where everything has mass 1. And so the red points are the new points that were added. So here's our 3 pictures just for comparison. So this top left one is the original Diaconis-Fulton edition with random walks. This one is rotor-router model, and this one is divisible sandpile. Okay, so there are several natural questions that these pictures bring up. So what happens if we run these models on smaller and smaller lattices? Is there some limiting shape? And if so, can we describe what it is? And in particular, is it the same limiting shape for the 3 models? It certainly seems from these pictures that, there's some little fluctuations at the boundary, but basically these 3 shapes look pretty similar. So the difficulty when thinking about something like this is, if we want to identify the limiting shape, somehow the most naive strategy would be, let's just define a model directly in RD, which would somehow correspond to the discrete dynamics, and show that, well, whatever that model gives you, that's the limiting shape. Unfortunately, it's not so clear how you would define this model directly in the continuum. So it turns out, this took us a while to come up with this approach, but it turns out that the right way to think about the scaling limit is, instead of thinking about the shapes themselves, you should think about what we call the odometer function. So for the divisible sandpile, let's let u of x be the total amount of mass emitted from the site x. That's what we call the odometer function. And the key property of this function is, if you look at its discrete Laplacian, so the discrete Laplacian of a function at a site x is defined as, it's the average value of the function at the neighbors of x minus the value at x. And so the key point about this is, well, so each term here, u of y over 2d, so the site y, whenever it gets any mass and sends it to neighbors, it always sends an equal amount to each neighbor. So u of y over 2d is exactly the total amount of mass that y sends to x. So when we sum over the neighbors, we get the total amount of mass that x receives. And u of x, by definition, is the total amount that it emits. And so this So this discrete Laplacian is just going to be equal to this function, which is minus 1 on the intersection of the two sets. It's 0 on the symmetric difference, and it's 1 on the outside. Right, because the points in the intersection, they started with mass 2 and they ended with mass 1. So you have a difference of 1. Points in A and B in the symmetric difference, they start and end with mass 1. So there's no change. And points on the outside, so if here's our set A plus B, which is the Diaconis-Fulton sum, these points started with mass 0 and they ended with mass 1. Whereas out here it's also 0. So here's how we're going to get a handle on this odometer function. So we know it has these Laplacians. So let's start out with a function which has the same Laplacians. So you can construct such a function like this. So first you take the function minus x squared. So this is just the Euclidean norm. And that function so the function x squared just has Laplacian 1 everywhere. And then we're going to subtract from it some sums of Green's functions. So here g of xy is the Green's function for a simple random walk in ZD. So it's the expected number of visits by a simple random walk started at x to the site y. And in Z2, where a random walk is recurrent, we need to use the recurrent potential kernel instead. And the point of constructing this function is so that it will have Laplacians similar to the odometer. Okay, and then we consider what's called the least superharmonic majorant of this function gamma. So among all functions in the lattice which are superharmonic and greater than or equal to gamma, we take the pointwise infimum of those. And then I claim that the odometer function is just going to equal the difference, s minus gamma. So this approach, I should emphasize, isn't something we just pulled out of thin air. So this is, so these kinds of things are studied quite a lot in PDE, where this is called the obstacle problem with obstacle gamma. And I want to quickly go through the proof of this claim because it's very simple and somehow this is the key step which allows us to identify what the scaling limit of the models is. So let's let m of x be the amount of mass present at x in the final state. So we know that the odometer function u, its Laplacian is the final mass minus the initial mass. So that's given by m minus this sum of indicators. And m is less than or equal to 1, because every site ends up with mass at most 1. On the other hand, gamma, maybe I'll just write down what gamma is, so we have it. So on the other hand, this gamma has Laplacian. Well, we've got a minus 1 coming from the x squared. And then because the Green's function is harmonic, so the function g of x, y, considered as a function of y, is, or let's say considered as a function of x, is harmonic away from x, and it has Laplacian minus 1 at x. So these terms will contribute exactly this 1a plus 1b to the Laplacian. So when we take the sum u plus gamma, we get a superharmonic function. And also u, so remember u is the odometer function, it's the amount of mass emitted. So in particular it's non-negative. And so u plus gamma is bigger than s, right? So s was S is the least superharmonic majorant of gamma. So u plus gamma is a superharmonic function, and it's bigger than gamma, and so it has to be bigger than S. So that's one direction. For the other direction, so let's consider S minus gamma minus u. So, well, S is superharmonic, and this inequality is actually an equality on the Diaconis-Fulton sum, because everything in the sum is fully occupied, and so m equals 1 on a plus b. So that means that u plus gamma is actually harmonic on a plus b. So this function is superharmonic on a plus b. And also it's non-negative outside a plus b. That's because, well, S is bigger than gamma by definition, and u, that's the odometer, that's the mass emitted. Outside a plus b, there's no mass moving around. So u is 0 outside. So we have a superharmonic function which is non-negative outside a plus b, and so it has by the maximum principle has to be non-negative inside also. And that proves the claim. So now that we've rephrased things in terms of this superharmonic majorant, we can define the scaling limit. So working in RD now, let's let A and B be some bounded open sets whose boundaries have measure 0. We're going to define a continuum version of this obstacle, so replacing the sums by integrals. We're going to take the least superharmonic majorant of this function gamma, and we're going to define D to be the domain A union B, union the set where S is strictly larger than gamma. And the reason we do this is, so remember the odometer function in the discrete case was just a difference S minus gamma. So our domain of occupied sites is precisely those sites where the odometer is non-zero, where some mass moved. So that's why we define our domain this way. So just to give a little visual intuition for this, here's a graph of the obstacle, that's this gamma, when A and B are two overlapping disks in the plane. So we're taking this function and then we're taking the least superharmonic majorant. So among all superharmonic functions that lie above it, we take the smallest one. And so somehow, visually what this represents is, imagine taking a big tablecloth or saran wrap or something and pressing it down over this surface in such a way as to minimize the surface area. So when the surface starts to curve down, the tablecloth will just lie right on top of it. But in this indentation in the middle, it's wasteful to have it dip down. So it saves surface area to have it lie flat. So there will be some region where the tablecloth lies strictly above the table. And that's the region which is the scaling limit of the sum of the two disks. So here's a related picture. So this is the obstacle where instead of starting with two disks, we start with 2 point masses at the center of the disks. And the tablecloth will separate from the table in the same region in both of these two pictures. So here's the corresponding Diaconis-Fulton sum of two disks for the rotor-router model. Okay, so we've identified what we think it should be the scaling limit of the models. So here's the corresponding theorem. So we have our two sets, bounded open sets in RD, whose boundaries have measure 0. And we want to run our models in finer and finer lattices. So we're going to fix some sequence delta n tending to 0, which represents the lattice spacing. And here's a notation. If A is a set in RD, let's write A superscript these points for its intersection with the lattice. So, okay, what can we show? So fix an epsilon greater than 0, and we're going to sandwich our sets between two epsilon neighborhoods, an inner and outer epsilon neighborhood of this domain D. So, well, first, so what is D? D is the domain we defined on the last slide. So it's the union of A and B with the set S greater than gamma, where the tablecloth is lying strictly above the table. This D sub and superscript epsilon are the inner and outer epsilon neighborhoods. And these sets Dn, Rn, and In are the Diaconis-Fulton sums of our two, so of the corresponding lattice sets, so the intersections of A and B with the lattice, computed using the three respective models.
So the width probability 1 only applies to one of them.
Right. So I wanted to state one theorem instead of three. So the price I pay for that is, so the divisible sandpile and rotor-router model are completely deterministic. So for those two models, you can ignore this with probability 1. So that's only needed for the original internal DLA model. So now there are various ways you can try to generalize or modify this result. I'll just talk about one of them, which is the case of multiple point sources. So that's like this bottom case here, where we started with 2 point masses. So let's fix some finite set of points in Rd and some positive real numbers, lambda 1 through lambda k. And then we're going to run our models in the lattices, delta n zd, starting with, so for each point xi, let's let xi points be the corresponding, the closest lattice point to xi, breaking ties to the right, say. And at the point xi points, we're going to start with this many particles. So we can do this with any of the three models, and we should get some scaling limit because we chose this number appropriately. And the scaling limit is, well, you can just think of replacing each of your point sources by a ball of the appropriate volume. And once you've replaced them by balls, then we're in the case of our original main result that was on the previous slide, where we're taking just the Diaconis-Fulton sum of 2, or in general n sets. And this, so when you take that Diaconis-Fulton sum, you'll get some domain D. And so if you started with multiple point sources, you can squeeze your discrete lattice sets in between epsilon neighborhoods of this D. And so once we prove the main result, this fact for multiple point sources follows from that and the case of a single point source. So I don't have much or really any time to talk about the proof. I guess let me just show this one slide which indicates a really broad outline. So the main steps are, so first we have some densities of starting particles in the lattice which are converging to some density of mass in the continuum. And from that convergence, we first want to deduce that the corresponding obstacles converge. So the obstacles are these functions gamma. In the lattice, they're defined this way, and in the continuum, they're defined using integrals instead of sums. Also, in the lattice, they're defined using the discrete Green's kernel, and in the continuum, they're defined using the continuum one. And so there's some Green's function estimates that you use in this first step. And then once you have that the obstacles are converging, you then want to conclude that, well, the odometer functions converge, because the odometer functions come from this this obstacle problem of finding the least superharmonic majorant. So that involves relating superharmonic functions in the lattice to superharmonic functions in the continuum. And then finally, once the odometers converge, then you want to get the actual domains of occupied sites converge. And somehow, intuitively, this maybe should be the easiest step because, well, the domain of occupied sites is just the support of the odometer. Even so, it turns out there are some additional technical assumptions you need to get from here to here. So converging functions doesn't automatically imply converging supports.
Which notion of convergence are you referring to in this sentence?
In the last sentence. Or any.
In each of these sentences.
So I can't go into too much detail, unfortunately. So this convergence is pointwise at all continuity points of the density. These convergences are uniform pointwise convergence. And this means essentially convergence in the sense of being contained and containing epsilon neighborhoods.
But the last arrow depends on some specific properties of the odometer function. It just doesn't follow. Functions tending to zero with huge support.
Okay, so unfortunately I have to skip a lot of these details of the proof. Okay, so just very briefly, so how do these ideas apply? So basically all of these ideas were developed first for the divisible sandpile, and then the question is how can you modify it for the other models? And in particular, at first it seems the situation for the rotor router seems not so hopeful because, well, we can define an odometer function analogously, just counting the total number of particles which were emitted from a site. But now, instead of having its Laplacian equal to 1, because of the rules for the way the rotors rotate, you can get these bounds that it's between -2 and 4. But somehow these bounds by themselves aren't good enough to give you anything interesting. So if you just try to naively apply the argument with those bounds, you'll get only that. So this is for the case of a single point source. You'll get that it's contained in a ball and contains a ball, but the radii are off by a constant factor. And the way we improve this situation is, instead of working with the odometer itself, we work with a smoothing of it. So just to get the idea, suppose we average the odometer function in a box. So sk of x is a box of side length 2k centered at x, and this v is just the average of u in that box. And then what happens is, if you consider the Laplacian of this average, so it turns out that you'll get much better bounds, essentially because Because you can represent the Laplacian as the divergence of the gradient, and when you do that, you'll get a lot of cancellation coming from the interior of the box, and you'll only get contributions coming from the boundary sites. And so you can get that, well, if you average over a box of side length k, then your Laplacian will be 1 plus an error of order 1 over k.
So the 1 over k comes from the fact that the boundary is of size proportional to k and the interior
Yes.
is of size k squared?
Exactly. And so then there's some trade-off. So I mean, this assumes that nothing strange is happening in this box. So in particular, the origin can't be in the box because that's where your particle started, and the Laplacian is not 1 there. And all the sites in the box have to be occupied. So there's some trade-off. If you use a really big box, then this condition is harder to satisfy. On the other hand, you get a smaller error term. So what we end up using instead of this box is a fancier version of the smoothing, which you can read about in our paper. But okay, so I just want to talk briefly about a lot of things which are still open. So first, for the rotor-router model, I mean, how round is it really? So if we look up until n particles have aggregated, so you take the difference between the in and out radii, and take the maximum difference over all times up to time n. So how fast does this function grow as a function of n? So here's some data. You can see even up to 1 million particles, the maximum value of this difference is less than 2. And it doesn't appear to grow very fast, even when n is increasing exponentially like this. So the ultimate conjecture, although it's not clear whether it's true, is maybe this difference is just bounded independent of n. This could grow like log n, or maybe even root log n or something. So we don't know. Another simple question which Laszlo Lovász asked us is, so is this set AN simply connected, or can it have a hole? So our result implies that if there's a hole, then it has to be very close to the boundary, so within log n of the boundary. Because everything, if you go closer than log n, the entire ball is occupied. But we don't know whether there can be holes close to the boundary or not. Another thing which would be very nice, and which is still quite mysterious, is the patterns in the picture when you draw the rotor directions. And there's certain modifications of the model which produce some more interesting shapes. So this picture on the left comes from, take all the rotors in this half-axis here, and instead of behaving normally, they always reflect. So rotors here, instead of pointing up, so all the up arrows in the stack are replaced by downs. So they'll go, they'll point right, and then they'll point down, and they'll point left, and then they'll point down again, and so on. And then in the row directly above it, it does the opposite. It reflects upward. So there they point, right, and then up, and then left, and then up. So the question is, what is this shape? And can you prove that it has a scaling limit? In this picture, the rotors on this half-axis are just broken, so they always point down. So we don't have any idea what this shape on the right is. The one on the left possibly is a cardioid, so a certain algebraic curve. But again, we don't know how to prove that. And here's a picture I made which attempts to understand these patterns. So in particular, it would be nice to understand, well, where are these points where you get these solid color blocks? And it turns out they're located at certain, so if you take the Gaussian integers in the complex plane and you apply a map, so you apply the map z goes to 1 over square root of z to the Gaussian integers, then you get a pattern which looks like the locations of these points. So here I've applied the inverse of that map to the rotor-router picture, and you get this picture, and you can see now these monochromatic regions are located at lattice points. So the question is, why are those points located at those particular places? We don't even have a heuristic explanation for why that would be. And finally, for the sandpile, there's some intriguing open questions. So let's fix an integer h, which is at most 2. And instead of starting every site in the lattice empty, we'll start it with height h. So if h is negative, that means there's a hole of depth negative h at that site. So if h is -1, for example, it means every site, when it first becomes occupied, then that just raises it to height 0, and then it behaves normally. So we can run the sandpile model with n particles at the origin when all the sites start with height h. And it seems from simulations that the limiting shape is a polygon, possibly a regular polygon, hard to tell, with this many sides. So, of course, you have to take h less than or equal to 2. So if h is 3, then already if you drop a single extra particle, then it'll never stop toppling. So that's the reason for this restriction. And the only thing that's known about this conjecture is the case when h is equal to 2. So a recent result of Fay and Rettig is that the limiting shape is a square. In all the other cases, even the existence of a limiting shape is not known. And even for h equals 2, you can ask, well, how fast does the square grow as a function of n, the number of particles? And that's also open. So I'll end with this slide. This just shows the sandpile started at heights 2, 1, and 0. So you can see the square for height 2. So for height 1, you get an octagon. This red part is the sites on the outside, which were started with height 1. My program colors those red. So it might look like a square, but actually the occupied site is this octagon. And here's the height 0 picture, which we've already seen, which looks like a 12-sided polygon. Thank you very much.
I've got one. Can you write down explicitly the scaling law for cases like if you have two disks intersecting, then you've got this characterization in terms of this minimal superharmonic function. Mm-hmm. Is there some sort of explicit analytic way of writing down what that shape is?
That's a great question, and we are wondering the same thing. So probably yes. In fact, we think it might be an algebraic curve of degree 4 in that case of two overlapping disks. But we don't know. We don't have any formulas. So something we're thinking about. Yeah.
If you if you have broken routers,
yeah.
let's say randomly chosen points in the plane.
Uh-huh.
Say every third point is broken.
Uh-huh.
Do you know what happens in that case?
No idea.
Have you done simulations to see if it has any effect?
Oh, I'm sure it has a big effect. But, well, so broken meaning that they always point...
Always point in the same direction.
And does the direction depend on the point or not?
Yeah, they're just stuck.
Like it's random directions? Or
Right.
stuck at
Only
random direction.
So maybe if they're stuck at random directions, then maybe it roughly cancels out. So I don't know. I have to think about it.
And it's interesting, there may be some critical densities where
Yeah.
really there's more.
Unbroken doesn't matter, right?
Sure. If you have one or finite number of broken ones, you can limit the damage.
Any other questions? Okay, well, let's make more.